Good morning, everyone. Now it's 9 o'clock, so we start our lecture. We're very happy to have been able to invite the Professor Kerri, Donaldson, Hanna to give us the lecture here. You will hear that what she talk about. I think that she will talk about some very exciting things about the lunar science. But first, I want to say a few words about Hanna, Professor Hanna. She's a planetary geologist, I would say, lunar geologist. And she got her bachelor degree in space sciences from Florida Institute of Technology. That means you're native for, how do we say that? We're
Floridian.
Floridian, yeah, native Floridian, yes. And after graduation, she went on to Brown in Rhode Island to get her master's degree and PhD degree in 2015. And afterwards, she went to Oxford as a postdoc and researcher for 5.5 years, from what I heard, yeah. And then she's here at now at the University of Central Florida, and she's starting a really big enterprise, I think, and especially that she just got a few years ago, got a very important grant from NASA for a mission to the moon. And I think that is very exciting. It's called a LunarWise, right? LunarWise. Yeah.
That's correct.
Okay. Yeah. Kerri, it's all yours now.
Great. Yeah. Thanks so much for inviting me to speak about LunarWise today. I'm excited to share about our mission with you. So yeah, I'm going to be talking about our mission to the moon, LunarWise, but I'll start off kind of giving an overview of kind of the geologic features that our mission is aiming towards investigating, and those are what we call the lunar red spots. And the lunar red spots were identified back early in the 70s using telescopic observations of the moon, just looking up at the night sky and noticing these really high albedo features that had unusual spectral characteristics as well as unusual morphologic shapes. And so these were deemed the red spots, and these are highlighted in the image on the left and by these red circles. And then if you zoom into some of those areas, we can see them on the right, and we can see some of their unique characteristics. One of them being that they're really highly reflective compared to the volcanic flows, the Mare flows surrounding them in each of the scenarios. We can also see that their morphology is quite different from the volcanic flows that are surrounding them. The Mare lava flows are very flat and very smooth, likely coming from very low viscosity magmas that had the ability to flow very far before they crystallized. But in contrast, these red spots have very steep slopes. They have very rough textures in some cases. And then we also see that the volcanic Mare flows have embayed these features, meaning they're surrounding these features. And so this would suggest that these red spots originated first, and then the Mare flows moved around them. And so what we're seeing today might not really represent how large these features are in general. They may be quite larger, but we can't really tell based on the fact that volcanic Mare flows have flown over top of them. Now they get their red name because of their spectral characteristics at ultraviolet and visible wavelengths. And so in this set of plots, what we're looking at is wavelength on the x-axis in each panel, and then we're looking at reflectivity on the y-axis in each one of these plots. The plot on the left includes spectra of red spots. The central plot also has red spot spectra. And then on the right, we're just looking at a range of other locations on the surface, including Alphonsus crater, Mare Humorum, Frau Muro, these are all areas just to do some comparisons. And when we look at the shortest wavelengths, so in the ultraviolet near 0.3 microns, and between about 0.6 microns, we see that for the red spots, we see this really steep positive slope. And so that means that the reflectance is increasing quickly as we increase in wavelength. And doing that comparison, we don't see that in other terrains. And so spectroscopists liken these features as red spots because they had this very distinct red slope, so positive slope as a function of wavelength. These early observations were followed up by orbital observations, and those included additional higher spatial resolution imagery data sets. And so here we see better spatial resolution observations of the Gruithuisen Domes. This is the Gamma Dome on the left, the Delta Dome on the right. And again, when we look at these features, we see that their shapes are very different than the lava flows that are surrounding them. They have very steep slopes. They have very flat tops. And just these shapes alone would suggest that the lavas forming these you would expect them to be much higher viscosity, meaning the lavas couldn't flow very far before they crystallized and formed these features. Additional observations came from the lunar prospector, which we can see in this middle plot here. What we see is the gamma and the delta dome of the Gruithuisen Domes shown as these black circles in this thorium plot at the top, and then this iron map in the bottom. And we see that for the Gruithuisen Domes, we see an enhancement in thorium. And we also see that these features are very low in iron. And then finally, we got observations from the Diviner Lunar Radiometer instrument, which is currently on board the Lunar Reconnaissance Orbiter. And that instrument measures what we call the Christensen feature position, which is a thermal infrared spectral feature that can be used to look at silicate mineralogy. And highly silicic materials tend to have very short Christensen feature positions. And if we look at this map again of the Gamma Dome and the Delta Dome, we see that all the pixels are very blue. And if we look at our scale bar, we see that these are all very short wavelength Christensen feature positions. And so this really builds up the story that we see these features that have unique morphologies. We see that they also have really unique compositions compared to the surrounding mare, and that they are enriched in thorium, they're enriched in silica, and that they are very low in iron. And these are all consistent with similar features that we see on Earth when we look at terrestrial rhyolitic and andesitic volcanic features. And so here's just a couple of examples of volcanic features that are highly silicic on Earth. We can see Mount St. Helens, which is in the United States, up in Washington State. And then we can also see Chaitin Volcano, which is in Chile and South America. And these features, we have a fairly good understanding of how they form on Earth, but we want to know, why are we seeing features like this on the moon? And part of the reason why we want to know is because on Earth, when we see things like Mount St. Helens and the Chaitin Volcano, we typically find them in subduction zones. And so in this diagram here, this set of volcanoes that we're seeing over here on the right, those would all be in subduction zones where you have the oceanic lithospheric plate being subducted below this continental lithospheric plate, this water-quenched plate that's being subducted. As it's being subducted, it's heated. That drives the water off, which we can see in this diagram. This percolating water goes up through the dry mantle material, heating it up, and also lowering the melting temperature of the material. And in doing so, allows for silicic magmas to form and then erupt onto the surface of Earth. Now, we see that there's two kind of key points here for these silicic magmas to form on Earth. One is that we have to have plate tectonics occurring, and also that water is really important for driving the magma at melting enough to form silicic magmas. But on the moon, we don't have water. And we don't have a lot of interior water or on the surface, and we also don't have plate tectonics. And so then that begs the question of how do we get such evolved silicic magmas on the moon? And so scientists have come up with kind of two main theories that have been used to explain how silicic magmas might form on the moon. The first is silicate liquid immiscibility. And this hypothesis really sprung from analyzing the samples, the Apollo samples, and identifying quartz-rich clasts within the Apollo samples. And analyzing those, they came up with this idea that what could be happening on the moon is that you have a basaltic magma coming up and intruding into the bottom of the lunar crust and continuing to melt until they're almost completely melted or have evolved in such a way that they're almost completely melted. And at that point in time, the melt separates into two different liquids. You get a very highly silicic and potassium-rich granitic liquid, and that separates from the iron and rare earth element and phosphorus-rich magma. And these two are immiscible, and so they're completely separated from one another. Now, the thought is that this is really great for explaining the amount of highly silicic magmas that we see in these Apollo samples and in these very small clasts. But it's hard to imagine in this scenario how you might create large domes on the surface of the moon or enough magmas to form some of the features that I was showing you earlier in the slides. And so I would say the most prevailing hypothesis for how the lunar silicic feature is formed is through basaltic underplating. And here's a diagram from Justin Haggerty et al. Showing what occurs during a basaltic underplating. And this is essentially where you have basaltic magmas intruding into the anorthositic crust here. That magma heats up the anorthositic crust and continues to melt starts melting the anorthositic crust, which then forms highly silicic magmas that are low in density and are able to make their way up through the fractures in the crust and extrude onto the surface, forming rhyolitic domes. And because we're using basaltic magmas and because we're using the anorthositic crust, we don't need to come up with mechanisms or we don't have to worry about enough magma being formed in this way. This process would generate large enough amounts of magma to form the silicic volcanic features that we see at the lunar red spots. But one key point that I want to make is that for both of the hypotheses that we were just talking about, the silicate liquid immiscibility as well as the basaltic underplating, assumes that these red spot features are rhyolitic or granitic in composition. And if we were to look at the standard diagram that geologists use to distinguish different rock types based on their silica content, we can see silica increases as you move to the right. And so highly silicic materials are over here. And in fact, rhyolites and granites are the most silicic materials or rock types that we find. But we don't actually know that these red spots are rhyolitic or granitic in nature. And in fact, they could actually be andesitic or dacitic in nature. And that's because we don't actually know how silicic these magmas are. The lunar prospector data that we use to identify the iron content and how enriched in thorium these features are have really large spatial footprints. And so the lunar prospector spatial footprint is actually much larger than many of the silicic features. And so the composition of just the silicic features are really difficult to resolve within a lunar prospector pixel. And so it doesn't really give us a true measurement of the composition of the domes by themselves. And when we were talking about the Diviner lunar radiometer data, the Diviner thermal infrared spectral channels, there's only 3 of them, and they were selected to map the global silicate mineralogy of the moon, not to map the composition of silicic features. And so we can use the Diviner data to identify where highly silicic materials are, but we can't use Diviner to distinguish how silicic one feature is from another, meaning we can't really use the Diviner data to distinguish between an andesite, a dacite, or a rhyolite. And so this is where our mission comes in. And this is the Lunar Vulcan Imaging and Spectroscopy Explorer, also known as Lunar VICE. This mission was selected as part of NASA's PRISM 2 program, and NASA specifically chose the landing site to be the Gruithuisen Domes. And so we developed our science investigation to land at the domes because that's the site NASA selected. This will be part of CLIPS task order CP21, and it will be a 10-day surface investigation in 2027 to understand the formation and of the silicic rich domes. And we really want to be able to test hypotheses there so that we can answer the question of, did the domes form by silicate liquid immiscibility, basaltic underplating, or maybe some other mechanism? Now, I know I also on this slide gave you a lot of acronyms, but I promise to explain all those acronyms in the upcoming slides. So the first acronym, CLIPS, is the Commercial Lunar Payload Services Program. And this program has NASA working with aerospace companies to deliver science and technology to the lunar surface. And so essentially, NASA works with the CLIPS providers to deliver payloads to the lunar surface. So NASA is essentially buying a ride to the moon through this program. Some of the CLIPS providers include Astrobiotic, which you might have heard of because they had a launch in February of this year, Deep Space Systems, Draper, Firefly, Intuitive Machines, which also had a mission in February 2024, Lockheed Martin, Ceres Robotics, Sierra Nevada, SpaceX, and Blue Origin. And so this is the new paradigm for how NASA intends to build the lunar economy and to get routine operations and instruments to the lunar surface. Here is a map. This is an image that was taken from a NASA presentation. You'll see in the lower left-hand corner here that this was updated on February 2023. So it's slightly old. And so while all of these landing sites are correct, don't pay attention to any of the dates, because some of the dates have indeed shifted in the past year. And so what this map is showing is all the upcoming CLPS deliveries to the lunar surface. And it in fact includes where the Astrobotic mission launched in February of 2024 was supposed to land. And so here we see provider Astrobiotic. It was supposed to land in Sinus Viscitatis, which is right here. And so it was actually supposed to land just near the Gruithuisen Domes. But of course, there was a failure shortly after launch, and they were not able to softly land on the moon and instead came back to Earth and re-entered the Earth's atmosphere. This also shows the IM-1 landing site at Malapart A, and so which is down here, but we can see the Intuitive Machines logo there. So they did in fact soft land again. That was in February 2024, just to kind of show how off the dates are on the plot. But yeah, you can see that in the next coming few years, NASA has a lot of spacecraft and technologies that are going to be landed at the surface. And that includes the Viper rover that will be going to the south pole of the moon. And then it includes our mission, Lunar Vice. They'll be going to the Gruithuisen Domes. So as I mentioned, our Lunar Vice instrument suite was selected through the NASA PRISM program, and PRISM stands for the payloads on the surface of the moon. And so in this program, NASA's essentially soliciting for research institutions and companies to develop suites of instruments and technology demonstrations that can be put on landers and rovers to go to the lunar surface to address very specific science goals related to understanding about how the moon has formed and evolved over time. Once your instrument suite is selected, those instrument teams work with NASA to define requirements for lander and rover capabilities. And then once you have those requirements defined, then NASA solicits the CLPS providers to come up with proposals to provide rides to the moon. And those proposals have to include a rocket that launches the entire thing to space and to soft land on the moon. It includes operations at the lunar surface, and it includes making sure all of our instruments are safe and work properly. So far, NASA has selected instruments to go to 5 different landing sites through the PRISM-1 program call. 2 missions were selected, Lunar Vertex, which will be going to Raynor Gamma, and then also the Farside Seismic Suite and the Lunar Interior Temperature and Material Suite were selected to go to Schrodinger Basin. And then in PRISM-2, Lunar Vice was selected to go to the Gruithuisen Domes. And then the Lunar Explorer instrument for space biology applications, also known as LEIA, was selected to go to the south pole of the moon. And then finally, most recently in the PRISM-3 selection, the DIMPLE mission, dating an irregular Mare patch with the Lunar Explorer, was selected to land at Aina and look at that irregular Mare feature. So our Lunar Vice science and exploration investigation includes one overarching science goal and one overarching exploration goal. And our science goal is to really understand how lunar silicic volcanism works as typified by the Gruithuisen Domes. And so to do this, we have two main objectives, and that is to first map any local variations in compositions that we see at the dome. And we want to be able to be like true good field geologists and correlate any of those compositional variations that we see to rock and regolith properties, to surface features, and any dome morphologies that we observe. And then our second objective is to provide context for all of the orbital data sets that we have in hand of composition and thermophysical properties. So we want to relate what we learn at the domes, so at the surface of the moon, to all of the orbital data sets that have been collected over the past decades. And then our overarching exploration goal is really to understand the geotechnical properties of the lunar regolith at the Gruithuisen Domes. And so we'll be leveraging expertise that we have here at the University of Central Florida to do that. We have two main objectives with that. We're going to first map any natural variations of regolith properties that we see. And then we also want to characterize how mission operations affect the local regolith geotechnical properties. And so that means as we're landing, we want to see how the lander plumes scour and loft the dust and alter the photometric properties of the landing site. And we also want to see how driving our rover around and using its wheels to dig into the regolith, how that affects the regolith properties of the dome as well. And so to conduct our mission, we have a suite of instruments that are on a lander, and then we also have a suite of instruments that are on a rover. But I'll describe the lander instruments first. And so we have two cameras that are going on the lander that are being built by BAE, which was formerly known as Ball Aerospace. And so we have a context camera, which we can see in this diagram here, that will sit on top or near the top of a lander. And this camera has the ability to take panoramic scans of up to 270 degrees. And so that will allow us to characterize the landing site throughout the lunar day. And it will also allow us to take images and movies of the rover as it's moving about the landing site so that we can see, again, how the rover is interacting with the local terrain. And we can, again, look at the geotechnical properties of the regolith. And then we'll have a descent camera that we can see here. This is a CAD drawing of a descent camera that will be nadir facing so that as we're landing, we'll be able to get images of the landing site, which will help us confirm our rover traverses that we're going to be following. And then it will also allow us to characterize any changes to the landing site from the lander itself, as we've seen from the Apollo landers, but then also here with the Chang'e landers when the U2 rover was just put on the lunar surface. And then, of course, we also want to characterize any changes as the landing is occurring, so any dust that's lofting. Now, you'll notice here that this drawing of a lander, or sorry, yeah, of a lander is very simplistic. That's my drawing, and that's because we are still in the phase of working with NASA to define our lander and rover requirements so that NASA can solicit the CLIPS providers for proposals to build our lander and rover. And so those proposals are supposed to come in over the summer. And so we should have a lander and rover provider by fall of this year. And I will not any longer have to use my silly simplistic drawings here of the lander. Instead, we'll actually know what our lander looks like because we'll have the lander and rover provider selected. On The rover, we have two main instruments. We have the gamma ray and neutron spectrometer, which here is in this CAD drawing that we have on the back of the rover. And then sitting on top of the rover will be two multispectral cameras, LV-VIC and LV-Cirrus, which will be co-aligned and sit on the same rotation stage within this enclosure. And they will rotate together and have the capabilities of doing 180-degree scans when we get to our locations across the dome. This diagram gives you just a basic sense of how the field of views for both cameras look. And assuming that our rover is 1 meter off the ground, that means that our cameras will see out to about 3 meters out in front of it. And you can see in this table spatial resolutions that at about 3 meters from the rover, that's where we'll have our best spatial resolution. And at those distances, we will have sub-centimeter spatial resolution, which will be really fantastic for mapping composition of rocks and regolith. And again, this is just my simplistic rover drawing to take place of not having our rover selected yet. So a little bit more details about the rover instrument suite. So again, we have two cameras that are embedded in the same enclosure, LV-VIC and LV-Cirrus. Combined, we call that instrument suite LV-VIMS. And you can see here's our CAD drawing of the two multispectral cameras, LV-Cirrus and LV-VIC. LV-VIC is the visible near-infrared imaging camera that is designed to map the composition at visible and near-infrared wavelengths. And so specifically, we'll be looking for iron-bearing minerals because at those wavelengths, visible and near-infrared, the minerals that you can detect are those that have some amount of iron in their crystal structure. We'll also be using LV-VIC to do just basic imaging and build up a sense of textures and morphologies of the rocks and the domes themselves. We have 7 spectral channels on LV-VIC, and you can see that they're listed over here in this table. Each one of these spectral channels have been chosen to be similar to spectral channels that have already flown on multispectral orbital data sets. So things like Clementine and the Lunar Reconnaissance Orbiter camera, the wide angle camera, as well as Kaguya spectral or multiband imager. And so we wanted, again, to be able to take what we're measuring at the surface and compare that to our orbital data sets. And having spectral channels similar to those previous orbital data sets will give us that ability. Our thermal camera is LV-Cirrus, or Compact Infrared Imaging System. And we'll be using this multispectral thermal radiometer to map composition. Similar to Diviner, we will be looking to identify the CF position of highly silicic materials, but then we'll also be using a wide range thermal infrared channel that will give us the ability to map temperature and also thermophysical properties. And over on the right, you can see here the spectral channels that we're flying. We are flying channels that are, one of them overlaps with Diviner, that's the 7.8 micron channel, but then we also have 2 spectral channels that are at shorter wavelengths that will give us the capability of distinguishing between different silicic contents or silica-rich contents. And this instrument, LV-Cirrus, actually draws heritage from another thermal radiometer that BAE BAE is building called LV-Cirrus that will be going to the south pole of the moon as part of another PRISM package on the CP-22 lander, and that lander has yet to be selected. Now here is the CAD drawing for our gamma ray and neutron spectrometer, LVGRNS. The gamma ray and neutron spectrometer is designed to have the ability to measure potassium, thorium, and macroscopic thermal neutron absorption cross-section. And we'll also be able, if there is iron, we'll be able to get detections of iron, and we'll also be able to place constraints on the lower bounds of hydrogen if there's any hydrogen enrichments or water enrichments at the domes. We have two separate sensors. We have the gamma ray sensor, which has a diameter of 2.5 inches, and then we have a neutron sensor that has a diameter of 2 inches. And so we'll have the full capabilities of measuring gamma rays all the way through neutrons. And this design is built on heritage from Arizona State University's mini neutron spectrometer that was on board LunaMap that launched on Artemis 1 back in November of 2023. And this is led by Craig Hargrove. And so, as I mentioned, we really do want to understand how silicic volcanism works on the moon. And so to do that, this diagram kind of shows how we're going to use our instrument suites on the rover to distinguish composition and determine the type of rock that is making up this volcanic feature. And so first, we're going to take the silica content from our thermal infrared spectra, as well as the silica abundance from the gamma ray and neutron spectrometer, and we'll also get constraints on iron content from our visible and near infrared system, as well as our gamma ray and neutron spectrometer, and that will allow us to determine the silicate composition and the rock type. Is this a rhyolite? Is this a dacite? Is this an andesite? Once we have that determined, you can see we can kind of flow in either direction, either to the left or to the right. If the rock types comprising the domes aren't as silica rich as rhyolite, meaning they're either dacite or andesite in nature, then this immediately will tell us that we have to think of other mechanisms that could be creating these dome features, like partial melting or some other mechanism. However, if the rock type that is making up the dome is rhyolite in nature, then we can use the thorium abundance from the gamma ray and neutron spectrometer to distinguish between the two main hypotheses, because we would expect low thorium for silicate liquid immiscibility formation, and we'd expect high thorium for the basaltic underplating. And so this is how we'll use our measurements to really test these hypotheses. So as I mentioned, our overarching science goal is to understand composition, and to do that we have an objective of mapping local variations in composition and correlating that to our rock and regolith properties, surface features, and dome morphologies. And so again, this is how we're going to do that through thermal infrared spectroscopy and gamma ray and neutron spectroscopy. Here, what I'm showing is how we can use the thermal infrared signature to distinguish between silicate composition using our thermal infrared radiometer on board the rover. And so we're going to be looking for this feature that I mentioned earlier called the Christensen feature. And that is this peak that we see in the spectra in this plot here on the left. And so what I'm plotting here are silica-rich rocks like pumice, rhyolite, and obsidian, which are these first three spectra here that have peaks closer to 7.5 microns. And then I'm also showing spectra of Apollo regolith samples, so Mare and Highland samples that show CF positions at much longer wavelengths. And so what the spectral plot is showing is that silica-rich rocks, like what we're going to be looking for at the domes, have much shorter CF positions than the more mafic-rich materials like the lunar soils. And so we can use the CF position to distinguish material types. And work by Jack Salisbury in the late 80s showed that you can take it one step further by if you have the CF position, which now is on the y-axis, you can take that CF position and you can derive what he called the SCFM index, which is simply just a ratio of the silica content divided by the sum of silica, calcium, iron, and magnesium. And doing that, you can see this really beautiful relationship between CF position and this index. And so if we can measure the CF position, we will be able to distinguish the silica content and the rock type using this relationship that I'm showing here. And it's really nice because we have two different instruments and two different ways of doing composition that are totally independent of one another. And so we'll be able to get silicate composition from the thermal IR instrument, but then we'll also get supporting silica and iron data from the gamma ray and neutron spectrometer. And it'll be nice to have these two independent measurements of those things. And then on top of it, we're also from the GRNS going to get thorium. And again, thorium is going to be how we distinguish between our formation mechanisms. As I mentioned, I'm just going to go over this briefly. We'll be using our thermal infrared wide range channel that will allow us to map temperature throughout the lunar day, which will allow us to build up an understanding of the regolith properties, including porosity and thermal inertia. So we'll be able to link those two. And this will be really important because from our orbital data sets, we have such a large spatial resolution that a lot of times we get contributions from rocks and regolith in a single pixel that we're identifying. But for lunar Weiss, because we'll be able to drive right up to a rock and we'll be able to drive right up to regolith, we'll be able to identify the thermal inertia for a rock independent of the regolith and see how they mix together to compare to the orbital data sets. And this is just highlighting how we're going to do our science at the surface of the moon and then compare to the orbital data sets so that we can really get the most out of our data sets and apply it to the other silicic red spots that I was showing you earlier in the talk. And then this is just, again, hitting on our exploration goal that we're going to do with our cameras on the lander and also on the rover, looking at how the regolith property changes as we drive across the dome and as we work at the dome. We have selected our landing site, and we are going to, in fact, land on the Gamma Dome. So here's the Gamma Dome and the Delta Dome, and we're looking at an LROC WAC image with slope data plotted over top of it. And where we are landing is where this green box is, which I'm now showing here in the perspective view. And so you can see our landing site. It's this, it's hard to tell, but it's a star with our landing ellipse and then our rover traverse. And so you'll see that this landing site and rover traverse really gives us access to this small fresh crater that's about 150 meters in diameter, that has exposed a really dense boulder field. And so our interest is really to drive as close to this boulder field and to the edge of this impact crater as we can, and also drive over to the edge of the dome so that we can look out onto the mare below, and to look over to the Delta Dome. We have designed a notional design reference mission where we have identified 6 different locations where we plan to rove to at the lunar surface, so that we can conduct our science investigation. And we're now working on developing strategies for having a robust yet flexible plan, depending upon how things go and also depending upon where we land within our landing ellipse. And then this is just showing that if we go to the edge of the dome, we will have a view of the surrounding mare below, which is what we see here. And then over to our left is the Delta Dome. So we aim to be able to capture data of both of those for comparison purposes. And this red line here is showing where the Astrobotics Peregrine lander would have landed had it softly landed at the surface. So where are we at now with LunarVice? LunarVice successfully passed our critical design review, or our CDR, with NASA, and that was held at the end of January 2024. We are currently under development. All now long lead items have been purchased and individual components are undergoing functional and performance testing, and we are on track for an on-time and under budget delivery in place in 2025. And as a team, we're still working to characterize our landing site and really understanding how to prioritize measurements during our 10-day surface investigation. And so just to summarize, LunarVice will determine the composition and rock type of the Gruithuisen Gamma Dome, and we're going to measure its thorium abundance. And doing this will place critical constraints on its formation mechanism. We have a 10-day surface investigation that will be in 2027, where we're going to investigate pristine regolith and boulders on this summit of the Gamma Dome. And we look forward to using our in situ measurements to provide a critical link to existing orbital data sets. And with that, I'll thank you. And I can take any questions.
Yeah, thank you so much, Kerri, for describing your very wonderful mission so carefully.
Thank you.
So, one question I have is that you have orders in optical and infrared spectrum, right? Spectroscopic range. Why don't you have a UV wavelength?
Yeah, that's a great question. Yeah, so because of the way PRISM is currently developed, we are on a very short timeline for building instruments, which would require having instruments that are already in hand, that are small enough and have the technical readiness level high enough that we could build them on budget and on time. And when we were looking for instruments, we did not see one, at least within our colleagues, at the ultraviolet wavelengths. And so the shortest wavelength that we could stretch out to is 400 nanometers with our visible camera. But so, it's unfortunate because a UV camera would be fantastic.
Okay, Kerri, I have to go to another meeting now, but I will ask my colleague James to take over to host this, to field the rest of the questions. But I can see that Tracy, are you there? Tracy Liao Yin?
Oh, yes. Yes.
You want to ask Kerri the question about the UV observations?
Not really UV. I think it's about the 950 nanometer spectra, because it's somehow, because I did some literature research about that, but it's hard to find that. Yeah, the types of.
Why don't you ask Kerri now?
Yeah, I think that would be great. Yeah, thanks. yeah, it's just because I am now involving in a payload mission held by Taiwan, another university, and it's for the name is for the UV telescope um on the lander, which will be on the I don't know, maybe a spot on the lunar surface. Yeah, but the one main purpose is to observe, just to get the multispectral imaging for irons and titanium. Yeah, just
Mm-hmm.
as you showed in some slides. Yeah, but it's just because the wavelength we're covering is from I think it's I forgot, but the end is till 950 nanometer. Yeah, and and then because we want to have some data, like the historical data, and then it's because it's easier for us to to know how we can design our instrument, and then later for the collaboration. Yeah, and somehow I couldn't find the like the spectra of irons and titaniums on at the 950.
Oh, interesting. Yeah, so did you try the Clementine data? Were you able to find the 950 nanometer band of Clementine?
Oh, I haven't dig into the. Is it? I need to I need to go to the PDS.
Yeah, if the US Geological Survey website, the USGS, has a
Yes.
really great site which has all the Clementine data that's really
Oh.
easy to download. I find that one a little bit easier to use than the
Mhm.
PDS, but the PDS should also have it as
Ah.
well. But yeah,
Uh-huh.
you might try the US Geological Survey.
Oh, great. Thanks. Yeah, because I was just I'm just reading the paper of Lucy uh Lucy et al. In, that's the very old paper in 1998. Yeah,
Yeah.
about his
Yeah.
algorithm. Yeah,
Yeah,
for
that's a great
deriving
one.
the yeah
Yeah, that's a great one to start with
and
for sure.
yeah. It's just I find it because I don't have that background, and I just for me it's a bit. I think I need some time for that to understand how this yeah how they develop these kind of algorithm, and then to to
Yeah, the thing
calculate.
yeah, the thing that's interesting about Clementine is Clementine was really designed to be a technology demonstration. And so I think what Paul Lucy did early on was he took what channels there were, and it was just fortuitous that there was good channels for doing mafic mineralogy on the moon. And so he took what he had at hand and used a lot of lab data and said, how can I best look at iron content but also take into account how space weathering affects the spectra and really disentangle iron and titanium from any effects of space weathering. And so he really utilized just the band passes that he had, and then also looking at a lot of lab data of the Apollo samples.
Oh, okay. Okay, thank you. Yeah, thank you very much.
Yeah, no problem.
Hi, Professor Hanna. Here is James. So I will
Hello.
host the next part of this seminar. So
Okay.
here I see the Lin Qihong have a question. Lin Qihong.
Hello, Professor. Can you hear me?
Yes, I can hear you. Hello.
Okay, so thanks for your great talk, Professor. So my question is, we know that compared to rock composed of the heavy element, the rock composed of the light element have lower resistance to thermal stress, radiation erosion, and micrometeoroid impact, etc. So does this mean that silicon-rich stones erode and disintegrate faster than other lunar structures? And if so, will this hinder the rock analysis? because when the lunar rod disintegrates, it may reveal the surface under another surface will be exposed, which may lead to the loss of the meaningful geological evidence. So this is my question. Thank you.
Yeah, it's interesting. Yeah, so I think when you read through a lot of the literature, the assumption when we're looking at the lunar surface is, obviously when we're looking at any part of the electromagnetic spectrum, that is only really sensing the uppermost portions of the regolith. And so most people assume that regolith is derived from the materials that are below it, and that there is likely some amount of mixing, but most generally it is like what was ever below it, and so that the rock essentially broke down and stayed in place. But that's only an assumption, and I think having drill cores where we can do some tests against compared, like take a drill core near a boulder and see like how the surface underneath of that compares to the boulder would be an interesting test for your question.
Yeah. Okay. Thank you, Professor.
Yeah. Thank you.
Okay. Does anyone in the audience have any questions? We still have some time to have a question. So here, I have a question. You have mentioned the CLPS, the Commercial Lunar Payload Surface Project, right?
Mm-hmm.
And I noticed that the list currently included only the American company. So will this program continue? Or if so, is there a possibility that it could be open to company from other countries, or there could be the potential for the international cooperation?
Yeah, that's a great question. I think that someone should pose to NASA, because I'm not entirely certain what NASA's plans are for that. But certainly we see a lot of private companies in lots of countries that are building up and wanting to have opportunities to test technologies. And also to build things like landers and rovers, or parts of landers and rovers.
Yes.
But I haven't heard NASA talk about how they see the CLIPS program evolving over time. And so that would be a really great question to pose to NASA to see what their view is on this.
Mm-hmm. Okay, I think I will focus on this part, this issue. Yeah.
Yeah.
Thank you, Professor Hanna. So
Yeah, thank you.
Any question? Any other question? It's almost 10 o'clock. The final call for the last question. Anyone have a question? So if not, I think it's about the time. So let's thank Professor Hanna again. And thanks for your wonderful presentation. So see you at the next minimum seminar series. Thank you, Professor Hanna. Thank you.
Yeah, thank you so much for inviting me. It was great chatting with you all. Have a good day.
Have a good day, too.
Thank you.